What is the most important point of the lesson so far? That if your series approaches zero as you go to infinity, then the summation of that series might converge. And might is a key word here because we've seen examples where they diverge, and we've also seen some where they do converge. So how do you know if it's going to converge or diverge? The terms must go to zero fast enough. If they go to zero too slow, as in the harmonic series, then we end up with a divergent um, series. However, if they go to zero fast enough, meaning the terms are getting smaller in a rapid pace here, then they do converge, as we've seen with some other ones. So these next few lessons, we're going to explore some different methods that test how quickly terms are going to zero, and try to find some criteria of what we can use, what kind of tests we can use to see if the series converges or not. So far, some of the methods that we know are the geometric one. So in geometric, if your R value is less than 1, the absolute value of it's less than 1, then it converges. Whereas if it's greater than or equal to 1, it's a divergent one. We have our P series. If the exponent on our n is anything bigger than 1, it's going to converge. If it's less than or equal to 1, if it's equal to 1, it's the harmonic one, then it diverges. So those are the ones we know about so far. We're going to look at some other ways to do that today. One of those being the comparison test. So what we're going to do with this comparison test is suppose that we have two series, A and B, with positive terms. B is convergent, and A is less than B for all n, then A will also be convergent. So what we're looking at here is if you have a graph, and this is our B right here. This is our series B, and it's decreasing fast enough that we know it's going to converge. If you have one less than that, that's also got to be going to zero fast enough. That one's going to converge as well. The opposite of that would be if we have another graph here that is not approaching fast enough. Say it's the harmonic one, where we know this is not going to get to zero fast enough. Then if you have a one that's bigger, another one that's bigger than that, that one's also not going to approach fast enough. So that one would also be divergent. So with the comparison test, you're going to check one and then see in relation to the other one, does it converge or not? Let's look at one example of this. The series 1 over n to the 5th power, we know is convergent by P series because our P here is 5, which is greater than 1. So this is definitely a convergent series. What if we want to know if this series right here, 1 over n to the 5th plus 4n cubed, is convergent or not? Well, this series is always going to be less than 1 over n to the 5th. For example, if we would plug in, say, n is 2, this is going to be smaller here because on here we'd have 2 to the 5th power, which is 32. Over here, this is also going to be 32, but if we add something else onto that that's positive, as in this case, it'd be another 32, because 2 to the 3rd power is 8 times 4 is 32. 1 over 64 is definitely going to be less than 1 over 32. The bigger the denominator, the less the value of that's going to be as a fraction. So that's going to be true that this series is always going to be less than this series. Well, we know from above that this one's convergent. So if that's convergent, anything smaller than it's also going to be convergent. So we know on this one that this series is also convergent. by comparison test to p-series. So that's how we would describe it, that we know that's true.